We know how the universe began, not with perfect certainty, not with the kind of precision that eliminates all remaining questions, but with enough confidence to build an entire cosmological framework on top of it. Approximately 13.8 billion years ago, in an event we call the Big Bang, the universe emerged from an extraordinarily hot, extraordinarily dense initial state and began expanding. The cosmic microwave background radiation, the faint thermal afterglow of that initial fireball, fills the sky in every direction with almost perfect uniformity, and its temperature and fluctuation patterns match our theoretical predictions with a precision that would be humbling if we were capable of humility about such things. The expansion of the universe has been measured, confirmed, and refined by multiple independent lines of evidence. The abundance of hydrogen and helium in the observable universe matches the predictions of Big Bang nucleosynthesis. The large-scale structure of galaxies and galaxy clusters matches our simulations of how density fluctuations in the early universe would have grown under gravity over billions of years. We know where the universe came from. What we do not know, what we have never known, and what keeps theoretical cosmologists awake in the particular way that only genuinely unresolved problems can, is where it is going. We know the universe had a beginning. We do not know if it will have an end, and if it ends, we do not know how. What follows is every serious answer physics has ever produced to that question, arranged not by likelihood, but by the particular flavor of dread each one generates. And then there is the heat death. It is the oldest proposed end of the universe and remains the one most cosmologists consider the most probable outcome given current observations. The second law of thermodynamics states that the entropy of a closed system never decreases. Entropy is, loosely, a measure of disorder, of the number of possible microscopic configurations consistent with the observed macroscopic state of a system. The universe began in a state of extraordinarily low entropy, a smooth, almost perfectly uniform distribution of matter and energy, and has been moving toward higher entropy ever since. Stars form, burn, and die. Black holes consume matter. Galaxies collide and merge. In each of these processes, usable energy is converted into waste heat, into photons distributed ever more uniformly through an ever-expanding space. The process is irreversible. You cannot unburn a star. In the incomprehensibly distant future, all stars will have exhausted their nuclear fuel. The last red dwarfs, the most parsimonious burners in the universe, will flicker out in approximately 100 trillion years. What remains will be stellar remnants, white dwarfs slowly cooling toward absolute zero, neutron stars, and black holes. Over timescales that make 100 trillion years look like a Tuesday afternoon, even these will fade and evaporate. Protons, if they are unstable, as some theories predict, will decay on timescales of 10 to the power of 40 years. Black holes will evaporate through Hawking radiation on timescales ranging up to 10 to the power of 100 years for the largest ones. When the last black hole has evaporated, the universe will contain nothing but a thin, cold, perfectly uniform gas of photons and other light particles expanding forever into an ever colder void. No gradients of temperature will exist anywhere. No usable energy will remain anywhere. No physical process that requires an energy differential, which is every physical process, will be possible anywhere. Time will continue, but nothing will happen in it. The universe will not end. It will simply become a place where nothing can ever happen again. This is the heat death. It is not dramatic. It does not announce itself. It simply arrives over the course of quadrillions of years like a tide that never recedes. The second end is the Big Rip. In 1998, two independent research teams measuring the distances and recession velocities of Type 1a supernova discovered something that the physics community was not prepared for. The expansion of the universe is not slowing down. It is accelerating. Something is pushing space apart at an ever-increasing rate, and we have no idea what it is. We call it dark energy, which is a name that means precisely nothing beyond acknowledging our ignorance. It makes up approximately 68% of the total energy content of the universe, making it the dominant component of everything that exists, and we understand it essentially not at all. One of the possible behaviors of dark energy, depending on its precise nature which we have not determined, is that its density could increase over time rather than remaining constant. If this is true, the repulsive effect of dark energy grows stronger as the universe expands. Eventually, the expansion rate increases without bound. Galaxies are torn apart, then solar systems, then planets, then atoms, then the subatomic particles that make up atoms. In the final fraction of a second before the Big Rip singularity, the expansion rate becomes infinite and spacetime itself is torn apart at every point simultaneously. Every structure in the universe, from galaxy clusters down to quarks, is shredded by the exponentially accelerating expansion of the fabric of space. The Big Rip does not leave a cold, empty universe behind it. It leaves nothing at all. Not empty space. Nothing. The calculation of when this would occur, if the dark energy equation of state has the right value, places it approximately 22 billion years from now, which is close enough on cosmological timescales to be genuinely unsettling. The third end is the Big Crunch. Before the discovery of accelerating expansion, the most widely discussed end scenario was the Big Crunch, the time reversal of the Big Bang. If the total mass energy density of the universe exceeded a critical value, gravity would eventually overcome the expansion, slow it, halt it, and reverse it. The universe would begin contracting. Galaxies would approach each other. The cosmic microwave background radiation would blue shift as the universe contracted, heating the sky. Eventually, everything would be compressed back into a singularity of infinite density and temperature. The Big Crunch is now considered unlikely given the observed acceleration of expansion, but it cannot be entirely ruled out. Some models of dark energy allow for a future transition in its behavior that could cause expansion to decelerate and eventually reverse. Additionally, some cyclic cosmological models propose that the Big Crunch is not an end, but a transition, that the collapse of one universe generates the conditions for a new Big Bang, producing an endless cycle of expansion and contraction. In these models, our universe is one iteration in an infinite series, each cycle potentially having different physical constants and different large-scale structure. The Big Crunch is terrifying not because of what it destroys, but because of what it might imply, that the universe we inhabit is not the only one, not the first one, and almost certainly not the last one. The fourth end is vacuum decay. This is the scenario that theoretical physicists discuss in the particular hushed tone reserved for ideas that are both rigorously supported and genuinely terrifying. The Higgs field, the quantum field associated with the Higgs boson discovered in 2012, permeates all of space and gives particles their mass. The current value of the Higgs field is what physicists call the vacuum expectation value, the value at which the field sits when space is empty. Precision measurements of the Higgs boson mass and the top quark mass suggest that the current vacuum state of the Higgs field may not be the lowest possible energy state. It may be a metastable state, a local minimum of the Higgs potential energy, sitting above a lower energy true vacuum state, separated from our current state by an energy barrier. If this is the case, quantum tunneling could spontaneously create a bubble of true vacuum anywhere in the universe at any moment. This bubble would expand outward at the speed of light. Inside the bubble, the Higgs field has a different value, which means the masses and interaction strengths of all fundamental particles are different, which means the chemistry that allows atoms and molecules to exist is different, which means everything is different in ways that are fatal to every structure that exists in our universe. The bubble wall traveling at light speed carries no warning. It cannot be detected in advance because no information can travel faster than it. Every point in the universe it passes through is restructured instantaneously at the most fundamental physical level. Stars, planets, living things, and the atoms they are made of are not destroyed in any conventional sense. The physical laws governing their existence simply change to values incompatible with their continued existence. They do not explode. They do not burn. They simply stop being possible. The vacuum decay scenario is particularly disturbing because it is, within the framework of our current understanding of particle physics, a genuinely open question whether we are currently in a metastable vacuum. The answer depends on precise measurements that we do not yet have the experimental capability to make. The fifth end is the Big Freeze distinct from heat death, a subtly different scenario involving the specific behavior of quantum mechanics in an eternally expanding universe. As the universe expands and cools, quantum fluctuations in the vacuum become increasingly important on cosmological scales. In an eternally expanding universe, these fluctuations will eventually produce, by pure random chance operating over infinite time, every possible configuration of matter and energy, including configurations that spontaneously assemble into complex structures. This is the Boltzmann brain problem, the disturbing statistical prediction that an eternal universe will produce more isolated, disembodied, conscious minds fluctuating into existence from the quantum vacuum than it will produce through the conventional process of cosmological evolution and biological development. The Big Freeze is the thermal state in which this becomes the dominant mode of existence in the universe. If existence remains a meaningful word for a universe in which the only events are random quantum fluctuations in a cold, dark void. The problem with the Boltzmann brain scenario is that it undermines the foundations of rational inference. If most observers in an eternal universe are Boltzmann brains with false memories, then the universe is not eternal. Then our memories of a consistent physical universe may be hallucinations, our scientific observations may be random fluctuations in a disordered vacuum, and the entire framework of physics we have used to arrive at this conclusion may be a coherent illusion generated by a momentary fluctuation in nothing. The sixth end is the cosmic phase transition induced not by the Higgs field but by some other quantum field we have not yet discovered or fully characterized. String theory and other frameworks for unifying quantum mechanics with gravity propose the existence of additional scalar fields with complex potential energy landscapes containing many local minima. The universe could be sitting in any of these minima, and quantum tunneling could cause a transition to any lower energy state. The landscape of string theory proposes something in the range of 10 to the power of 500 possible vacuum states, each corresponding to a different set of physical laws. A transition from our current vacuum to any of these would be indistinguishable, observationally, from vacuum decay and equally fatal to everything that currently exists. The terrifying implication of the string theory landscape is that the specific physical laws we observe, the constants, the particle masses, the force strengths, are not fundamental. They are local conditions. They are the particular minimum our universe happens to be sitting in, out of an astronomically large number of alternatives. And there is no principle we know of that guarantees our minimum is stable. The seventh end is the collision of our universe with another. The inflationary cosmology that explains the uniformity of the cosmic microwave background and the flatness of the observable universe generically predicts eternal inflation, a process in which inflation continues indefinitely in regions of space outside our observable universe, constantly producing new bubble universes with potentially different physical properties. In this framework, our universe is one bubble in an enormous or infinite sea of bubbles, each expanding into the inflating background space. Collisions between bubble universes are not merely possible in this framework. They are predicted to occur. A bubble universe expanding from a nucleation event that occurred near our own bubble's nucleation event would expand toward us and eventually collide with our cosmological horizon. Such a collision would leave an imprint on the cosmic microwave background, a distinctive pattern of temperature variations that some researchers believe they have detected as the CMB cold spot, though this remains controversial. If a bubble collision with sufficiently different vacuum properties reached us, the consequences would be similar to vacuum decay, a region of space with different physical laws expanding into our universe at light speed. But bubble collision also raises the deeper question of what it means for our universe to have a boundary, for there to be something outside our space-time. For the physical laws we consider absolute to be local conditions in a larger structure whose properties we cannot observe or predict. The eighth and final end is the one that does not fit neatly into any of the previous frameworks because it does not emerge from the known laws of physics but from their incompleteness. General relativity and quantum mechanics are the two foundational theories of modern physics. They are separately the most precisely tested theories in the history of science. They are also fundamentally incompatible with each other. Attempts to quantize gravity, to construct a quantum theory of the gravitational field consistent with general relativity, have not yet succeeded. String theory, loop quantum gravity, and other approaches have produced elegant mathematics and interesting predictions, but no confirmed observational signatures. The singularities at the centers of black holes and at the Big Bang itself are points where general relativity predicts infinite density and curvature, and where it simultaneously breaks down and produces nonsense. We do not know what happens at these singularities because we do not have a theory that is valid there. It is entirely possible, and some physicists consider it likely, that the correct theory of quantum gravity, when it is eventually constructed, will reveal that the universe does not work the way we think it does at the most fundamental level. It may reveal that time is not fundamental but emergent. It may reveal that space is not fundamental but emergent. It may reveal that the distinction between the beginning and the end of the universe is a feature of our approximate description rather than a feature of reality. The end of the universe may not be an event that occurs in time. It may be a realization about the nature of time itself. A recognition that the framework within which we have been asking the question contains a hidden assumption so wrong that the question dissolves when the assumption is removed. And perhaps that is the quietest and most unsettling possibility of all. Not that the universe ends in fire or ice or the tearing of spacetime or the slow cooling of the last photon, but that the universe and the time in which it exists and the laws by which it operates are approximations to something we have not yet understood. And the true end, if there is one, is something for which we do not yet have the mathematics to describe, or the language to name, or the conceptual framework to even recognize when we are looking directly at it.